All right, recording is rolling. It is Wednesday, January 15th. Okay, so got some school announcements we're going to look at. Then you guys have your rotational inertia lab out from yesterday. Okay, we got all the data yesterday. We're going to put the graph together today. I'll help you guys out with that. And then we'll figure out how to interpret that and figure out what's the rotational inertia of that pipe system. That was the goal. Okay. And then I'm going to pull up the PowerPoint of these poster slides. We'll do some review of concepts you guys have seen so far. And I got one new concept, which is kinetic energy. And I'll show you guys some applications of that in physics. Okay. Now, you guys' physics puzzles, chapter 8, I gave you guys a few days ago, but see, possibly tomorrow, I think might be a good time for me to give you guys some time to work on that. Okay. All right, let's look at school stuff. Oh, club picture day is this Friday, so it's 2 days from now. So if you're in a club, pictures. I know that's how it's worked in the past. Is there's been schedules go around where made it like different times for different clubs. Usually in the gym, right? This is what it's been in the past. It's probably like that. Right? Okay. And then there's also a senior panoramic for Friday. So if you're a senior, then show up at school wearing whatever you want to wear. That's going to show up in the panoramic. In the past, they usually do that first period, so I'm gonna guess they probably did again. Right? All right. Principals Council. So I got an email. This is from Miss Legate. All right. It says, I'm looking for, you guys ever look up here? It's might apply to you, maybe. I'm looking for students to serve on an advisory council. The goal is to get a cross-section of students to participate so I can get a wide view of student issues and possible solutions when needed. We'll meet monthly with the council to discuss upcoming VHS events, policies, anything else that I'd like to discuss. Right? So if that looks interesting to you, let me know and I can put your name in. Oh, yeah. Oh, yeah. Yeah. Oh, see? All right.
I'm also interested.
Yeah.
Put me down.
All right. I will
Down.
put all three of you guys down. Yeah. All right. Think you'd be good council members. So I'll write that in there. All right, let's get. Oh, of course, we have a 3-day weekend coming up. So I do need to get you guys your next quiz pretty soon, rotational dynamics. So working on that, and almost have it together. And then, of course, you guys got a 3-day weekend. That's plenty of time to work on that. All right, you guys ready to finish this lab? Finish this lab? Okay. All right, so here. So before I start plotting points on this graph, which we're about to be doing, remind you guys of the setup from yesterday. All right, how this works. So I had a big old pipe system. I've taken it down since yesterday, but this big old pipe system, it was low friction. There's a little bit of friction, but not much. Right? So you could grab this central pipe axis and rotate back and forth, and there was some resistance to change in motion. That's inertia. In a rotational sense, call that rotational inertia. How much rotational inertia? How can I quantify that? So some number of kilogram meter squared in physics. How can I figure that out? Right? So we approach this 2 ways. One is we look at the geometry of this, right? And added up from the here, guys, look here. We're looking at that rotational inertia table, and we added up all the bits, but mostly these two arms. We said, okay, we got an estimate just from the geometry. All right, then we put this thing in motion and gathered a bunch of data. What do we get? So we measured 4 things. What's the radius of the central pipe? Got like close to a centimeter, I think it was. Right. That was constant. Although that was controlled. What are these lab weights that were hanging? Now that was the independent variable. So over there yesterday, I was changing out different lab weights. Right? What's the distance that it falls? That was about 70 centimeters, I think. And then you guys were timing that, and I asked you guys how much time you guys would stopwatch. Right? We did like 3 trials and took an average for each one. Right? That was all the measurements, or just those 4 columns. That was all the measurements. Now then we did a number of calculations. So we said, what's the linear acceleration of this lab weight falling? Right? Now that goes back to kinematic days. You guys remember those kinematic formulas? So if you know how far it falls and how much time at the stopwatch, and it starts from rest, you can solve for A, and it works out to 2x over t squared. We did that. Okay. Now, guys, this lab weight falling, some linear acceleration, is that related to this whole pipe system rotating, speeding up, spinning, which is angular acceleration, and they're related by this r. So that's turntable physics. So we did that, A over r. Okay. What's the tension in the string? Which was pretty much just the weight itself. We went through elevator physics and strictly got a more accurate number, but the idea, right? Torque is R cross F, right? And that was the last column on your table. Now, on this table, I have one more column, which is I, because we're relating up to what's rotational inertia. But I want to do it a better way with you guys. So I did not give you this as a column value, I. We're going to get that from the lab table. right, so let's go back over here. Okay, all right, you guys ready to make this graph? Now, I'm gonna put it on this page, get nice and big. Okay, now Nathan, you got some numbers, right? You guys, Nathan, you got different angular accelerations and torques. Okay, so we're gonna put together a torque versus angular acceleration graph. So on the vertical axis is torque in Newton meters, and on the horizontal axis is angular acceleration in radians per second squared. Okay, and there's a relationship between those two. We're gonna see what that relationship is. Okay, and so I gotta scale these axes. Got to figure out how big does it go, so I know kind of what space to put all the points. Okay, so Nathan, what was the largest torque yesterday?
That's 0.055.
0.055. Right. So we probably round that up to 0.06. I'm gonna scale this 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. Right, and you guys are doing the same thing. So scale the axis always starts at 0 for this class. Right. Guys, out in the real world, sometimes you'll see graphs that don't start at 0, but if you do, then be cognizant of that, because if you see like some jump in the graph, say like, well, what does that mean proportionally? Right. In this class, graphs always start at 0, so that there's like some change that you can very clearly see what that proportion is relative to 0. Right. Right. And then Nathan, what was the largest angular acceleration yesterday?
0.636.
0.636. Okay. So to round that up to say 0.7, let's go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 should contain all the data that axis. 0, 0.1, 0.2, 0.3, 4, 0.5, 0.6, 0.7. All right. And what was the torque on that one again? You said 0.06 something?
The torque?
Yeah, 0.05 something?
0.055.
0.055. All right, so we got the first point. All right, so here 0.055 is right about there. It's pretty close. Right about there. So this is the coordinate. 0.636, 0.055. Right. And then these have units, of course. This is radians per second squared. This is Newton meters. All right, got 1 point on the board. Right. Let's get the other 4 points. So, Nathan, what's the next coordinate?
0.445 and 0.044.
And 0.044. All right, so 0.445 and 0.044. It's pretty close to right there. Okay. 0.445, 0.044. Okay. We got radians per second squared and Newton meters. Okay. All right, what's the next point?
0.3 and 0.033.
0.3, 0.033. It's right about there. 0.30, 0.033. All right, so got radians per second squared, 8 meters. All right, next point.
0.136 and 0.022. Nathan responded.
136.022. Right about there. Okay. 0.136, 0.022. Okay, we got radians per second squared, 8 meters. All right, what's the last point?
0.075.017.
Okay, 0.75, 0.17. It's right about there. 0.075, 0.017. Okay, radians per second squared, 8 meters. Okay. Yep, that's what that should look like. Because those 5 points lie on a what shape? What's the trend of that?
Is that thing linear?
It is linear. It is linear. Yeah. Right. I think you guys may have guessed that yesterday too. Right. Because here. So if you don't want, I should have asked you guys, what's the best way? Should I connect dot to dot to dot to dot, or should I throw my ruler down and sweep a nice line of best fit through it? Yeah, line of best fit. Okay. Maybe some points are a little bit above the line, some are a little bit below. Actually, those are pretty well all in line. That's some good looking data right there. Okay. Uh, and you may have guessed even before collecting the data that it should have shown up linear because this corresponds to sort of a physics formula that goes how? I got torque and I got angular acceleration. I can say torque equals what? What's the relationship? Here, I'll give you a hint. It's analogous to Newton's second law of motion, F equals ma. Torque equals I alpha. Right? You guys are torque equals I alpha. Right. So there was two perspectives on torque. Torque equals R cross F. And if there's a net torque, it results in I times alpha. Right? Right. Now, right, so there's two details I'm thinking about this. One is, do you guys remember the goal of this lab is to figure out what's the rotational inertia of the system?
Yes, I do.
Ah, and if that's the goal, what property of this graph gives that answer? The slope. The slope. Yeah, rise over run, the slope. Because it's like torque equals I alpha. So if I pick 2 points on the line and do rise over run, that would give me the rotational inertia, and that would be the answer. That's it. So I'm going to pick these 2 points because these are pretty much on the line. Right. So let's go from the first point to the last point. We're going to do this rise over this run. Rise over run. Right. Now, so I'll say I equals the delta tau over delta alpha. Right. Change in torque over change in angular acceleration. Right. Since it's kind of crowded, I'll just do this on my calculator screen. But it's rise, so 0.055 minus 0.017. There's a change in torque, right? Then close that in parentheses, then divide by and open a new set of parentheses. Right? The run, change in alpha, angular acceleration, 0.636 minus 0.075. Okay? Oh, and you know what? Before I hit enter, right? Do you guys remember yesterday, before I even set any of that pipe system into motion, we did the geometry analysis, and we said we can come up with a pretty good guess. Let me dig through the notes from yesterday. We got a different set of notes for each class. It was right here. I was mostly focused on those two arms. You guys remember that? Okay. And I did it different ways. I got 0.04 kilogram meter squared. And I was guessing that this would be like a lower bound condition. So the actual answer is probably a little bit bigger than that, but it's probably, that's the ballpark to the answer, right? You guys think? Maybe 0.05, 0.06, maybe somewhere there, do you guys think? Okay. Let's see. Right, moment of truth. This is going to be about 0.04, 0.05, 0.06, somewhere there. Gonna find out. Hey, it is. Look at that. 0.068, I'll call it. That's kilogram meter squared. Right? And that's the answer. That's the answer right there. Okay. So I gave you guys a box on your lab that says I equals, and I gave you the unit kilogram meter squared. Guess what goes in that box? 0.068. Okay. Which is the slope of that graph. Okay. Guess that. Okay. Now, a couple other details about this, though. A couple other details. One is, I did, there's a little bit of a mismatch. You see, I'm using as a guiding formula. Oh, torque equals I times alpha. That looks like Newton's second law, rotation, right? And maybe line. This line does not exactly match with this framework because why? What's a little bit of a difference? Why does this not exactly match this?
Friction and other factors.
Frictional torque. Yeah. You guys see this intercept right here? This intercept? Right? That's exactly what it is. This is frictional torque. So isn't that like a y-intercept right there? Right? So we say plus frictional torque, right? To make that equation better match that graph. Right? Here's what I should have done yesterday. Now you guys are third period class, so I've had to try. Usually on my mistakes I'll make earlier in the day. My very first class, I put on I think this lab weight right here. I put on one that was too small and hung it on there, and the whole system did not move at all. Guys, how is that possible? How's that? I put on some weight and it doesn't even move. That only happens if there's what? Friction. Okay. So, guys, think about, because here's things that I want you guys to get from this class is to think about how things work. How do you interpret this? If you put on some weight, therefore it has some torque, and then it doesn't even move. There's zero angular acceleration. This is the torque you had to overcome to get it to move in the first place. That's how much friction there is. Okay. Now, if I write this out, because this is more like a formula, let's do this as an equation. Torque equals, I'm going to write the exact equation for this line right here. 0.068, that's kilogram meter squared. And that's multiplied by the angular acceleration. Okay. Plus, now here's where I'm going to guess. Just by eyeballing this graph, does that look about 0.012 maybe? Something like that? Okay. 0.012, and that's Newton meters worth of torque. Okay. And that expression right there. So I could go back to the pipe system yesterday. Okay. I could hang on any weight, right? Well, as long as it's big enough, gives enough torque, right? So anything, right? I can extend this even further to right. I can tell you exactly the motion of that pipe system because it's going to lie somewhere on this pink line, even if I put like a 1 kilogram weight and it's like way up here. Okay, right, set. All right. Here's the other consideration. All right, so you guys remember the PowerPoint version? It had a table that had a column for I. Right? Now, if you calculated it, you'd be missing this full graph and you'd be missing this y-intercept. Right? So that would boil back down to tau equals I alpha. Like if you have tau and alpha, if it was straight from a textbook, can you just divide tau by alpha and get I that way? Right? If you did that though, given this set of data, are you guys ready for a critical thinking question? If you did I equals tau divided by alpha, and you just did it that way, would you be overestimating or underestimating I, which is rotational inertia? Would you be getting a number a little bit too big or a little bit too small? Too big. Yeah. How'd you know it was too big? Yeah, right. Because here's an explanation I know is you can see it from the graph. Because if you just did torque equals I alpha, if you assume that this is the whole story, then you would be assuming that this curve does go through the origin. And let's say you had the origin at like this point here. And you said, okay, well, guys, if all you have is that point, you have nothing else to work with. Because then torque equals I alpha. And guys, look at how my ruler is angled right here. Wouldn't that be the line? Zoop, right there. And guys, what is the slope of this line going through a single point compared to the slope of the actual line going through all 5 points? It's too what? It's too steep. Yeah. Which hence you would be overestimating the rotational inertia. Right? You said? All right. All right. So that is close on that lab. Just make sure your lab page is in that grade tray by the end of today. All right. So you guys got the data from yesterday if you're here yesterday, and everybody has the graph, of course, because we put the graph together. You guys got all that? Yes. All right. The rest of class today, we're going to go to the PowerPoint, and here's what we do. First, I'm going to do a review of all of these slides you guys have seen so far, because this is kind of a human psychology thing, but every time you see something again, your brain remembers it better. You guys ever heard this as a study tip? If you haven't, then guys, here's a really good study tip. Guys, put your phones away. Phones away. Look up here. Think about this. All right. There's a math test coming up 2 weeks from now. Guys, should you wait until the night before the math test and study for like 3 hours and cram? That's not a good strategy. Right? Maybe you try that. It doesn't work very well. Right? What if you take the exact same 3 hours? You just kind of say, 10 minutes today, 10 minutes tomorrow, 10 minutes the next day. And so it accumulates to 3 hours. Does your brain remember it a lot better? Absolutely. It can be the same amount of time investment. Right? So that's what we're going to do right here. We're going to take a quick look at all these slides. And then at the tail end, I got a few new slides that are related to rotational energy. Okay? To energy. And so look here. The top half of this table, you guys saw last semester, that's kinematic motion, linear, rotational. Right? Then you guys see most of these, except for you guys see this very bottom row, 1/2 I m² squared. Right? This is going to be the new concept that I'm introducing today. This is kinetic energy involved in rotating that you guys are going to see today. Okay? So here's turntable physics. You saw last semester, and we also applied yesterday. Okay? For example, how far does the point move is related to how far this turntable turns. Just very simply multiply by its distance from the center. Guys, that very top formula, what's a specific application of this top formula that you guys have known since elementary school? One trip around the circle is called one circumference, right? And circumference equals what? 2 pi r? 2 pi r, right? Isn't 2 pi radians one trip around the circle? And now you can go any distance around the circle with this one, right? And here's how fast, and here's the acceleration, and we applied this bottom one yesterday, right? Right. Here's a rotational kinematic formula. So if a turntable's turning, how far is it turned? How fast is it turning? Maybe it's a function of time, right? Like that. Right. Here's the turntable, so let's just stop. Here's 3 graphs. You guys saw that last semester. Center of mass. You guys remember those foam boards the other day? You're figuring out what's the center of mass, right? Different techniques to do that. Here's the math technique you use on paper. It's a weighted average is all it is. What's a weighted average of the mass, right? That's all it says. Okay. All right. Stability. Some of these are a little bit bonus. All right. All right. You guys remember those rotational inertia sticks? Right? How much inertia did something have? Now, last semester, how much inertia was just how much mass, right? The more mass, the harder it is to get going and the harder it is to stop it, right? This week, so well, it's also how is that mass distributed? Something to do with mr squared, right? R is the distance from the pivot points. Okay. Right. Right. So here's some common shapes that could rotate or roll somehow, right? No, there's some aggregate effect of mr squared, but like suppose you have a spherical shell like this basketball. The aggregate effect is 2/3 mr squared. You can prove that with calculus, right? Parallel axis theorem. You're going to see this by the end of today. Guys, you're going to see an application of this for a ball rolling. You guys see this ball rolling across the floor? Because if there's a ball rolling across the floor, is it actually rolling about its center of mass, or is it actually rolling about the point where it's touching the floor? Point where it's touching the floor. Right. So you take the value off the table, 2/3 mr squared. Now, the 2/3 mr squared only applies if it's rotating about its center. You guys see this dashed line going through the center? It's kind of hard to see, but there's a dashed line going through the center. 2/3 mr squared. And you add to that the additional mr squared because it's offset by the distance r that it's actually rolling about. How much inertia does it feel like if you push the ball to get it to roll across the floor? Or if it's rolling towards you and you want to stop it? It actually feels like 5/3 mr squared. So it feels like, right? But hold on to that idea because you're going to see that by the end of class today. Can you guys hold on to that idea right there? Okay. All right. Torque, R cross F, turning a wrench, opening a door. Right? And we applied that yesterday. There was a torque. Right? Right-hand rule and matrices. Right. Now this slide and this slide, I'm really just showing you guys in case you take physics or engineering in college, you're going to see this. Because in this class, we're just going to talk about torque being clockwise or counterclockwise. But there's a mathematically better way to describe that. And it goes through the right-hand rule. Right. So I'll plant that idea here, and you might see that in college. Okay. Or this might be your job one day. If you're doing civil engineering, you're going to want to know those. Right. I did an example of, I did show you guys an example. You guys remember organic chemistry tutor? There was a YouTube video, right? Showed how to solve a cross product, right? Guys, equilibrium. What's your main 2 conditions for equilibrium? What goes to 0 and what else also goes to 0? The net force and the net torque. There you go. Net force, net torque. Right? And then you can say, well, that's also true along each axis. Right there. 2D, 3D. Right? Okay. Here was your lab back on Thursday. You guys remember Seesaw lab back on Thursday? Also, I applied this yesterday. You guys remember there was, I didn't know what the mass of one of the pipe pieces was. So I set up a meter stick and I did exactly this and figure out what the mass was. You guys remember that? Do that? Okay. And then here's your lab back on Friday. You guys remember the scaffold? You guys had a couple of spring scales, hold up a scaffold. Right? Okay. What's the tension in each spring scale? Now you cannot solve this with forces alone because now it depends on the location of this weight. If I shift this weight around, the individual spring forces change. Right? Guys, are the sum of the forces up equal to the sum of the forces down? Yeah. Right. Now that's true. Right? But each individual force you can only solve if you also include torque. Right? So you can only solve this with torque. Right? Right. Lab page from last week. Right. Here's a classic example. If you don't see this in this class, then you'll probably see it in college, though. Right. So ladder against a wall. Right. Again, there's different forces at different locations, so you have to solve this with torque. Right. And I'll show you exactly. There's the answer at the bottom. Right. Right. This was a warm-up question the other day. You guys remember this one? Right. Actually, one of your textbook questions. I think we'll do textbook questions tomorrow. It's probably a good day for that. Right. Looks like this. Actually, it's a little bit more complicated because your textbook also throws, I think, a little flag at the end. And that flag has some weight. And you have to consider that also. So it's like a little bit more involved version of this. Right? Right. If you wind a string around a turntable and pull a string, zoom, You're applying force at a radial distance. That's a torque. So R cross F. And that results in I times alpha, because those are your two perspectives on torque. R cross F, I times alpha. Okay. Also, this could be the cross section of that central vertical pipe yesterday. There was a string bond around that. Same idea. Okay. Also, if this turntable has some rotational inertia I, it's accumulating an angular momentum. L is I omega. That's analogous to P equals mv. You guys remember last semester with the collision carts, momentum was conserved, right? This is angular momentum, right? Okay, here's a lab we just finished today. Right. All right, let's talk about angular momentum. Angular momentum. So one classic example is ice skater. Now, angular momentum is conserved. So if the ice skater goes into a slow spin and then pulls their arms in, they spin faster. Zzz. The physics principle is angular momentum is conserved. Sum of L before equals sum of L after. L is I times omega. So if you shrink your I, you're going to grow your omega. Right? Hence, you'll spin faster. You see that? Right. Here's some extension questions on this. Guys, does it take some effort? Does it take some work to pull your arms in if you're spinning? It does. It does, right? What that means is, I'll put this as a question. Okay. Guys see those two pictures, left picture, right picture? Now they have the same angular momentum, right? That's the principle here. But which of those pictures is there more mechanical energy? The picture on the left or on the right? No, one of them has more actually.
On the right.
The one on the right has more mechanical energy, right? Now the total energy actually would be the same, right? But more mechanical energy because it came from that skater's muscles. If you pull your arms in, that takes effort. You're adding mechanical energy to the system. It comes from your muscles, right? And the physics formula that I'm leading up to by the end of the class today is 1/2 I omega squared for energy. So if I times omega is balanced on both sides, the fact that omega is being squared for energy, because 1/2 I omega squared, like it counts more. All right, so got that. Okay. Spinning a basketball, if you put a force at this radial arm, boom, pow, gives a torque. If you apply it for some time interval, maybe like a tenth of a second, pow, 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 pow. It's given an angular momentum. It looks like impulse, but in a rotational sense. You can solve for how fast is the basketball spin, right? Or if it was a different type of ball, then maybe this rotational inertia would be different. So the answer would be a little bit different, right? But it would look the same structure, right? More force, the faster it's going to spin, and so on, right? Here's a pair of graphs, torque first time, angular momentum first time. Now, both these graphs are different perspectives on the same story. They both tell the same story. Okay? For example, what if you wind a string around a turntable and pull it, zoom? Or what if you spin a basketball, zoom? You apply torque for some time. The area under this curve, that green rectangle, represents the accumulated angular momentum. Right. Now that graph, angular momentum is a function of time. The rate change of that is torque. Right. So both these graphs are telling the same story. Okay. All right. Some of these slides, like this one and the next two, are really made for AP. They're a little bit more involved. Right? But I'll do them real fast with you guys anyway. Here's a real classic AP question. You lower a stationary disk onto an already rotating disk, and they stick together. Right? The physics principle is that angular momentum is conserved. So if you make a graph, L versus T, angular momentum is conserved for the whole system, the two-disk system. Okay? That gold disk is going to start spinning once it sticks to the green disk. Hence, it's going to gain angular momentum. But it sort of like took it away from the green disk because the green disk slows down. Right? But the sum of these two curves is always the same. Right? All right, here's another classic AP type question. If you throw a blob of clay at a rotating rod, and this rod can rotate about this pivot point that I marked with an X. So you throw a blob of clay, sticks, and the whole thing rotates. How fast does it rotate? Could be the classic question. Right. So this is angular momentum, but what's the angular momentum of a point mass? Kind of a weird question. Right? So it's just regular momentum mv, and you cross that with this radial arm r. So it's r cross mv. Okay, so you know r mv. That's the angular momentum. That results in I times omega. Okay. You can solve for omega. Now, one last little trick here is this I is really, if it was a blob of clay that stuck to the rod, that's a combined I. It's both the I for the clay and the I for the rod. Get that. Okay. All right. All right. You guys ready for something new here? Rotational kinetic energy. Here we go. So this is your 1/2 I omega squared. All right. I'll show you guys some puzzles you could solve with this. You guys see this pail on this disc right here? All right. So everybody look here. All right. So I'll toggle back and forth. Notice I got the same scenario, but maybe two different perspectives, ways to approach this. Right. So there's a number of questions you could ask about this. Right. I could ask, how fast is the pail moving after some time? I could ask, how far is it moved after some time? I could say, how fast is it moving after falling some distance? Maybe those are the three classic questions, and there's different ways to go there too. Right? Now, the key here is that this disk up here has rotational inertia. I remember last semester, you guys remember last semester, those Atwoods we were setting up with pulleys, those Atwoods? Okay. Last semester, we were ignoring the mass of the pulley itself. We were saying, well, or sometimes I labeled it like massless and frictionless, and we just ignore that. Right? If you did that with this one, because if this disk up here has no mass and no rotational inertia, right? Wouldn't this pail just pure free fall? And this would turn back into the Galileo question, or something like that. Okay. Okay. But if this does have rotational inertia, it's going to slow the system down. Is it going to slow it down? Okay. So here's one approach. You could approach it with torque. You say, well, R cross F results in I alpha. Well, what is this force? All right, well, it's not quite the weight because you got to do elevator physics. Here's your turntable physics. Here's kinematic linear. Here's kinematic rotation, right? And depending on which question you get, this doesn't really lead to exactly one place because it depends on what question you get. Right? Right. But if I fast forward to the next slide, you guys see the next slide? Same scenario. Notice I set up an energy conservation. You guys see this? Right. Now, here's what I'm doing. I'm going to flip back to the last slide because I want to cover up the next slide. You guys know the next slide is conservation of energy, right? I want you guys to guess. I bet you guys can guess what specific question conservation of energy is really efficient at solving for this scenario. Right? Right. Now think to energy. Guys, everybody look here? Everybody think about this? Guys, if I ask you an energy question, do you ever see time involved in an energy question? No, I never see time involved. Oh, there is time taking, but it's not in the equation. Do you ever see a question about acceleration with conservation of energy? No. Do you see maybe a distance traveled, like a height change? Yeah. So that'd be potential energy, wouldn't it? Wait, okay. So maybe after that bucket has fallen some height change. It's what do you think the question could be? What is it moving? How fast? Because that could be kinetic energy, couldn't it? Right. Let's put it all together. Right. So the classic question could be, how fast is that bucket moving after some distance moved? Right. And here's the setup. Here's your classic conservation of energy from last semester. Right? And because the bucket falling is providing what type of energy at the top? Potential energy. So I jot down MGH. That's all the supply of energy. So equals. Okay? And after it's fallen some distance, it has what type of energy? Kinetic. 1/2 mv squared. Now, if that was the end of the story, then that's the Galileo question. But this is not the Galileo question, because don't forget, this disk rotating has some rotational inertia. It's going to slow the system down. Here's your new term right here. You see 1/2 I omega squared? That's new. That's rotational kinetic energy. That's the energy associated with rotating. You see that? Right? Now, next step. You guys see this V? Okay, see if you guys are following. What does this V represent? Yeah, the speed of the pail. That's the speed of the pail falling straight down. What does this omega represent? Yeah, how fast this disk is rotating. You guys see it? Okay. So is this V related to this omega? Like, guys, if the pail is falling faster down, does this disk have to be rotating faster to match that?
Yes.
Because they're both tied by the same string, right? They're tied together by a string. That leads to the next step. Because I only did one step between here and here. I only did one thing. I replaced this omega with V over R. Guess that? It's being squared. But okay. Now you do some more algebra. Skip some algebra. You can get exactly the speed of the pail. Okay. All right. And then, all right. I've got a bunch of slides that have balls rolling down hills. You guys see a bunch of slides, balls rolling down hills? Right. Oh, now the classic question is, what's the speed of the ball at the bottom? You guys that? And it's the same question over and over. Speed. You see, all right. So that's the classic question. What's the speed of the ball? Okay. And there's two ways to solve it. Here's the hard way. Here's the easy way. Let's start with the easy way. The easy way is conservation of energy. Guys, what type of energy does the ball have at the top? Potential energy, MGH. Boom, jot that down. Okay. What type of energy? Well, here, is this ball moving in a linear sense? Like if you point a radar gun at the ball, does it have a linear speed at the bottom? So that's 1/2 mv squared, so jot that down. Okay. Is the ball also going to be rotating? Yeah, if there's static friction, it will be. And that's this term right here, 1/2 I omega squared. You guys see that? All right. And there's your full equation. All right, you guys see where this comes from? All right. Next step is the linear speed of the ball related to also how fast is it rotating? Yeah. And that's this substitution right here, V over R, instead of omega. You guys see it substituted for omega? Did V over R? You guys see that? Right. And then the other substitution is what's the rotational inertia of the ball? You guys think the different balls are going to rotate differently going down the incline? Right. So I could go back to the rotational inertia table and say, well, for a basketball, that's a spherical shell. We'll call it 2/3 mr squared. Guess that? Right, everybody good so far? Right. Right, and then a bunch of algebra, you get that answer. Right. Right, you guys ready to see the hard way to do this? Right. Let's go back to this slide. Here's the hard way, is through torque. Right. Now, torque, you have to consider that there are different forces at different locations in the ball. Maybe there's its weight acting through the center, and there's this normal force, well, it's right here, and there's this friction acting at the edge. And you actually you do have to have the friction to induce rolling. If there's no friction, it wouldn't roll. All right, just have that. All right. So this is torque is I times alpha, and it's well, that's what it results in. But here's where it comes from. It comes from R cross F, so it's mgr sine theta. Right, put it all together. Okay. Now, guys, look at this step right in the middle in orange. Do you guys see an orange right here? 5/3 mr squared. Wait a minute. Wait a minute. In energy, I was calling it 2/3 mr squared, which came straight off that rotational inertia table. Isn't it 2/3 mr squared for basketball? Why am I saying 5/3? Guess where's the 5/3 coming from? You guys remember a ball rolling across the floor? You had to consider parallel axis theorem. You guys remember that? I said earlier today, I said parallel axis theorem is going to show up by the end of class. There it is. Promise fulfilled. That's, guys, this basketball is actually rolling about, not through its center, but about this point down here. Okay. Now, guys, here's the difference between these two methods to solve the same question. The energy method, you do not have to consider parallel axis theorem. The torque method, you do. Okay. So it's like sort of different rotational inertia from these different perspectives. Okay, it's kind of a weird corner of physics, but they give you the same answer. Look at that; it's the same answer either way. You see that? Okay, now that's for a basketball. What about for a solid ball? Like a bowling ball is pretty well solid, isn't it? Okay. Now it's the same procedure, but a little bit different answer because the mass is distributed differently. Right? Here's any ball or anything that's rolling down. Right? So I got some general I. You see this general I? You just pop in any I there. So now you have the answers to all these questions. Okay. Here's the last slide for this whole unit. Here's the last slide. Let's have a roll race. Okay, so I got an incline. Okay, now there is friction on the incline. You guys see this coefficient of static friction right here to induce rolling, except for one lane. I have one frictionless lane. I'm going to let an air hockey puck go down. Okay? You guys see the air hockey puck is going to beat everything? In terms of energy, it's mgh at the top, and it's only 1/2 mv squared at the bottom. And all the energy goes into its motion, so it's going to win the race. Okay. I should say all the energy goes into its linear motion. But all these other objects are rolling. And so some energy is diverted into making them roll. At least that's an energy explanation for why they're going to lose to the air hockey puck. Right? Okay. Do you guys see the rank order of these? Which is that the objects that have the mass concentrated more closely to the center, like this bowling ball, are going to beat the objects that have the mass distributed further out. And the object with the mass furthest out is that ring right there. Guess that ring, right? That's going to lose to all these other objects every single time. Right? How about this? A lot of times when you see this premise, they'll say, "Oh, equal mass and equal radius objects." Okay. If I go back a few slides, let's go back to say like the sorry, my screen's doing that. Okay, we're good. We're good. Okay, good. This right here. Okay, guys, does the mass of the ball or the radius of the ball show up in the final answer? Ooh, it does not. Right? Like it shows up in the middle equations, but it cancels off by the end. So what's important is actually not the mass of the ball and not the radial size either. It's how the mass is distributed. Okay. So if I go forwards, let's go back to this roll race. Because let's say you have a basketball next to a ping pong ball. Are those both spherical shells? The basketball and ping pong ball? What's going to win the race? Or do they tie? They tie. Because the mass and the radius cancel out. Right? All that matters is that they're both spherical shells. Right? How about this? What if I put a marble next to a bowling ball? I'm simplifying a little bit. Let's assume that those are both uniform spheres. The mass is distributed through, right, evenly. Right? That's not exactly true, but we're going to say that it is. Right? A marble next to a bowling ball. Which one of those wins? They tie again because they're both solid spheres. Okay, is it? Because what if I have a small cylinder next to a large cylinder, do those also tie? Yeah. Or what if I have a small ring next to a large ring? So it's how the mass is distributed, which shows up in this final answer is some fraction underneath that radical. But other than that, okay, the mass and the radius cancel out. Right? Okay, you guys good there? All right. So I've shown you guys how to solve a bunch of these. We've done a bunch of labs over the last few days. I think tomorrow is probably a good day to sit down and solve textbook puzzles in class. I think is probably a good allocation of time. And guys, all the textbook puzzles that I've assigned to you guys, you could solve with everything that you've seen so far. All right. So I think that's yeah, that's about where the bell's been ringing my other classes. You know, we got 5 minutes. Let me see if I got a bonus video for you guys.
Mr. Griffin,
Yeah.
did we get textbook puzzles?
Yeah. Here, I'll give them to you. All right. Let me pull up the video and I'll get you an extra copy here. I'm looking for a specific. Aha, here we go. All right, here's a bonus video for you guys. Or wait for the bell. All right.
This is a gyroscope. It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel. First thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright. When the wheel stops, the force disappears and the gyroscope falls. Incredibly, this force will support the gyroscope like this. It appears to be levitating.